Okay, can you hear me? Yes. All right, so I'm going to be giving a talk on something that I haven't talked about since a long time. I did not want to give a talk in this conference. And the idea was that people from Vienna will not give a talk, but then Francesca had a fair point, because this is a topic that Francesca, Carlo, and other people have been pushing the past 5 years. And I think it's very good that they're doing that. I really believe in this. I did this in my PhD studies, and I haven't really worked on it since the past 5 years. And unfortunately, a couple of very talented people that worked on this, like Tommaso De Lorenzo and Pierre, left the field. So Pierre is trying to come back, it seems.
Tommaso is a pillar of QISS as well, in other ways. So.
Yes, that is true. Tommaso is back also in another way. So Francesca asked me to, we didn't leave Francesca or Carlo give a talk, so somehow I had to talk about it, which I'm happy to. So, come on. As Francesca noticed, I'm going to refer to the recent nice review by Francesca and Carlo on the topic, because there is many things in it. There's many arguments and counter arguments, and I wouldn't be able to review all this in half an hour. I've also not followed them very closely. And I decided instead to focus on a simple geometric argument behind these ideas. Also because many people in this community are not going to be familiar with the technical details. Yes, so essentially what is the conviction? That somehow dark matter, what it is remnants. So black holes that evaporated down to Planck mass and have an exterior dimension of Planck area, 10 to the minus 70 meters squared. Now, okay. All right. So it all comes down to a definition of volume, a volume of a black hole, which was actually the first task that Carlo gave me as a student. He mentioned before in the discussion this thing. So the problem was, can we define a volume for the interior of a black hole? And what Carlo had said was, he noticed that, look, take Minkowski space, and I want a definition of the volume inside a sphere. And there is a cute coordinate independent way to say that, which is take all the surfaces of the inertial observers, so constant velocities, these diagonal lines there, and the maximum one is somehow in the middle. So this was a vague intuition, and can you carry this to the black hole case? And the way you do that is that you say take a sphere, and you maximize twice, or you extremize once and you maximize then. And you take all the extremal surfaces, which are defined as the surfaces that have zero trace of the extrinsic curvature. And then you find the maxima, the extremal surface with the maximum volume among them. Now, if you take the ideal case of a black hole that exists forever, so it's Schwarzschild geometry, and you take the event horizon here, you notice that you have this family of surfaces, some of them going to the left and to the right. They're all extremal, and there is one in the middle, a sort of limiting surface. And this one has the biggest volume, which is of course infinite, because the thing is infinite. And so the way you would make sense of this in the vacuum, in the eternal black hole case, is that you would take two spheres and take the difference, and then you see that you have a linear growth of the volume. Now, what this does is it captures the intuition that you've heard probably, that space and time change roles in the interior of a black hole. And this is really the essence of it, because if you think about it, take this sphere in Minkowski. So here we're in Minkowski, this black surface is giving you the volume of the sphere in the usual sense, but then ask yourselves what's the time of the sphere, the time duration of it. And if it's an ideal sphere, it's infinite, right? Because it's a word cylinder. And so the time goes from minus infinity to plus infinity. Similarly here, this is what's going on with the volume. The time is now bounded because it's a well-known fact that the time from the horizon to the singularity, to theoretical zero, is bounded by pi m. There is no geodesic that lasts longer. So time becomes compact and, well, bounded, and volume now can grow indefinitely. Yeah, a very quick way to see how you get that is take the Schwarzschild element, what do you take? You take an R equal constant surface, and then you take the induced line element, just take the derivative with R, and you're going to get this value, 3m over half, and this is where the surface is. So the bulk of the volume of a black hole lies at this value for the radial coordinate. Now, if you think of a more realistic situation, slightly, where you have some sort of collapse here, open Schneider or whatever, what's going on is that you get this QISS formula, which is that it's going to be some constant which depends on the details of the collapse, and the mass, the initial mass squared, times the time at infinity. So I'd like to say that as a cute trivia, that people are still using this formula in this really construction. There's even a review recently for this specific formula where they're calling it CR volume for Christodoulou Rovelli. And if there's anything that I ever did that's going to have my name, it's going to be this formula. Although I truly believe that the reason is that they think it's Rovelli and the other Christodoulou that is famous. That's fine. Yeah. But I will take that. That's fine. So to see how striking this whole thing is, take this example. First of all, consider a solar mass black hole, so 10 to the 30 kilos. It's going to need 10 to the 55 times the actual age of the universe to evaporate, so not very pertinent. And it would contain, if such a thing happened, well, maybe it is. We'll talk about Penrose's idea later. It would contain volumes equivalent to 10 to the 5 times our observable universe. So imagine, GR, inside GR, you have objects, you have solutions, where you take a sphere of the black hole horizon. It could shrink down to 10 to the minus 70 square meters, so Planck area, and inside you would have 10,000 times the volume of the universe. You might remember what Carlo was saying before, that it makes no sense to say that there aren't enough states in there. We'll come back to that in a moment. Now, it's more pertinent for what we're talking about to think of this case here, 10 to the 12 kilos. So I looked it up, Mount Everest is 10 to the 14 kilos, so 100th of the Mount Everest in mass, make it a black hole, then what you get is, well, what is it here? So what you get at the final stage of the evaporation, you have about a liter volume behind a Planckian area. Now, those of you who were careful would have noticed that I was talking about evaporating black holes, but I was showing you eternal black holes. So it is indeed the case, and it's in this paper with Tommaso, that one can use a very simple model for an evaporating black hole, something called the Vaidia line element, where you have a dependence of the mass on time at infinity, and what you get for the volume of this limiting surface is pretty much the same thing, plus some correction, which is not important. For large times, this is negligible. Now, the striking thing is that you can show in this geometry that these surfaces exist, and they exist until Planck time, all right? So take a moment to appreciate this. You have a geometry here which is describing a black hole, well, actually a trapped region. It's shrinking, it goes down to Planck mass after zillions of years, and this thing is at the same instant as the collapse, because there is a space-like surface that connects it. There is a sense of time, in which the complete evaporation is the same moment as the formation, and this has a humongous volume because it's going like m to the 5, because evaporation happens at time m cubed, and there's an m squared. All right, so here's an intuitive way that Carlo likes to use, which is imagine that this is a hypersurface I was talking about, and imagine that time is passing at infinity. What's going on in the interior of the black hole, close to this region of 3m half, where m can be time dependent, is that it's getting elongated, all right? It's really becoming longer. And it's shrinking in the sense that the radius is getting smaller, because the radius goes like the mass, and the mass is being evaporated. Now, okay, so then what happens to all that space? You have this remnant there. It has this macroscopic volume. It's a tiny, tiny, tiny thing. What's going to happen? If it just completely disappears at the end of the evaporation, you just lost that volume from the universe somehow. It's some sort of piece of geometry that disappeared. That sounds really weird. So one could think intuitively and try to demand that, Francesca, can you let me know when I have 10 minutes? Because,
yeah, sure.
Thank
You
you.
have still 20.
All right. So intuitively, one can simply ask that, well, we started off from flat space. Then something happened and collapsed. You got a black hole. Then, okay, the thing is evaporating and so on. It should go back to flat space in some way. Nothing lives forever, after all. But now you have a natural foliation, a sense of time, where in GR you can take whatever Cauchy foliation you want. And I just argued that there is a very natural one if you want to capture the evolution of a black hole, which is capturing this elongation inside. And so there's going to be a Cauchy surface in which somehow it gets stuck here, the evolution. So you have, you're describing in such a foliation the formation of the black hole to be as the same instant as any time on its horizon or trapped surface. And the speculation here, which was based on ideas that were being discussed in Marseille at the time with Carlo, with Alejandro and others, is that somehow you should have a phase which is going to release this volume. And there is this black shaded thing to represent that we don't know what we're talking about. But whatever this phase is going to be, it should be at least m to the 4, because from other arguments, this is what is expected to be the purification time. Now, we'll see in a moment that from the geometric argument I was giving you before, one could expect an m to the 5, a duration, which, by the way, Pierre put a paper out just a few days ago making this point, which was very nice to see. Because the way one can try to complete this picture of what happens after is that after the black hole phase, one gets a white hole phase, all right? And this is what is called the black to white spacetimes. Now, the idea here with the spacetimes is that one can create a sort of solution of the Einstein field equations by gluing various pieces of the Kruskal manifold. This is fine because of Birkhoff's theorem that tells you that this is the unique solution maximally extended locally, all right? But you can always build other solutions by gluing things together. And so this gives you something that solves Einstein's equations at any point, except a piece that is missing here, this thing here. This has been studied by Pierre and Carlo also with Hawking evaporation. Now, the point here, somehow what has been going on in loop quantum gravity, I will not tell you the details of it, but this is sort of what I was doing then as well, is that what is missing here is where you expect something non-perturbative to happen, and you want to plug in a quantum gravity amplitude, all right, to see what's the probability of this thing happening, what's going to be the durations involved here, and so on. And as a parenthesis, I'm putting this figure here with the little guys to make the point that there is a very nice physics here involved, because if you go through these trapped and anti-trapped regions, so that's black-white, or if you go from the outside, it's the same phenomenon, but if you go inside, it's going to be like seconds to get to the other side, and if you go from the outside, could be billions of years. So this is like a forward time travel machine, which in the early, I don't know what's the status of that, but it was thought that maybe, what are they called? Super fast radio bursts. One could see the signature of this effect here, but anyway. Yes, so I'm just giving you some stuff that I'm not going to explain here, but as I was saying, what one can do is build a transition amplitude using covariant loop quantum gravity, what is called spin foams, where one has objects of this kind, which are vertex amplitudes and phase amplitudes multiplied together with holonomies and SL2C group elements. Put some sort of bulk triangulation, have a boundary state that is encoding what's going on at boundary surfaces of space-time of this sort. So this gives you a sort of hole in the space-time that you try to fill with this amplitude, and you're going from black to white. There is, I'm giving you here some early works that I was involved in. There's various things that happened afterwards. I'm just giving you some representative citations. The point and the general moral, what people think is happening, and I'm not claiming at all this is some sort of solid result, but the indications are that you get some sort of exponential scaling for the probability of this to happen. That goes with some power of the mass suspected to be m squared. I'd like to make a parenthesis here that one thing that we wanted to do in QISS, and it's been 6 years, we haven't really done it, I think, at least, is to work on the interpretation of these probabilities and the amplitudes, because it's, it's really at the core of what loop quantum gravity means, and I don't think it's really done. So I don't really know what this probability means exactly, but what I'm saying is that if there was a meaning to it, it would scale like something of this sort. And what this tells you is that the probability is going to be order unit when you go to Planck masses. That's why one. There is a story that from quantum gravity, one can see that such remnants might be possible and might be stable. So I didn't really go into the arguments for why they're stable and so on, so I'll give you here the other facets of this. So first of all, how one could have such objects in nature. And this is one of the reasons that people, hear white holes and can be like, wait a minute, where is this thing gonna come from? Because you are gonna need some really strange initial conditions. Even though in the theory, one should note that black holes appear at the same time as white holes. So the Schwarzschild element is not the line element of a black hole. It's the line element of a black hole or a white hole. It's exactly the same. What I was just talking about essentially gives you the weird initial conditions to get the white hole at the end. Now, the idea is that maybe there's two possible origins there. This is fluctuations, strong quantum fluctuations at the very early universe that create regions of high density that collapse into black holes. As I was saying before, if you have things that are 10 to the 12 kilos that were formed then, they would be they would have completely evaporated now, and therefore, if they're stable, they would behave like dark matter. Okay, perfect, thank you. I'm almost done. Another idea comes from Penrose, which is that maybe what's going on is that it's the old black holes from the previous eons that did have abundant time to completely evaporate that came through from the Big Bang. Okay. Which I remember when Penrose visited in Marseille and we were discussing this, he was thinking that there's also evidence of them somehow in this paper, because this is some sort of circles in the sky, but I don't know what became of that idea. Now, yeah, there is an argument that is given by Francesca and Carlo that a combination of basic quantum theory assumptions and the fact that there is discreteness would stabilize these objects at Planck mass and the Planck area, like quantum theory stabilizes atoms because of discreteness of spectrums. There is possibly a different kind of phenomenology, because they would still be emitting very weakly this kind of things. Maybe one could see this radiation. And as Carlo was pointing before in the discussion, this story provides a very simple way out for the information paradox. So the remnant scenario has been discussed since many, many, many decades, independently of everything that I have said. It was sort of fell out of favor because of this kind of objection that, well, if you would have these objects, you know, the intuition is that you have this Planck mass thing, it doesn't really have degrees of freedom inside, and so if you take an effective field theory approach, you should have these objects being produced by the slightest perturbations, and that's the cornucopians objection. The fact that you have huge volumes inside, if this is an old black hole, so not something that was formed at Planck mass, but was formed at a larger mass and then evaporated, therefore it has a big volume inside, this basically doesn't apply. And information can simply go out from the white hole phase. Now, yeah, like a year ago, I sort of went back to this with Carlo and Alejandro. We met at the QISS school, and there was this very simple idea coming out in this paper that maybe actually if these things are dark matter, they would behave exactly like dark matter, because we're talking about things that are Planck mass, so they're minuscule, 10 to the minus 70 square meters of area. They would interact only gravitationally, so they would really behave like dark matter, and they do have a considerable mass, which means you wouldn't need a large density of them. That's sort of the problem. It would be sufficient to have on average one of these particles per volume of our solar system, but we're moving very fast through the rest frame of the dark matter, about 100th of the speed of light. So it turns out that there would be, on average, about 1 per square meter per year passing. And one can think of a protocol, this is with Josephson junctions, where the delocalization of the wave function of the electron across the junction is sort of like the oscillators of Aspelmayer, if you want. So it's a delocalized wave function that is going to interact with a mass that is passing, and this can induce a current. And we're imagining a sort of detector that would catch these purely gravitationally interacting particles. This is not a collision-based thing. It's not ionizations and so on. Now, look, it's 3 theorists, okay? I don't think the reviewers were experimentalists, so I'm not putting my hand on the fire of how feasible this thing is, but it's certainly interesting that one could detect these objects, and they could indeed provide the explanation for what is dark matter. And yeah, I'll leave you with a summary. That was it. Thank you.